Welcome to this deep dive into the world of statistics. Today, we are exploring two concepts that are often used interchangeably but serve very different purposes: variance and standard deviation. While both measure the spread of data, understanding their nuances is key for everything from financial risk assessment to medical research. Imagine we have two groups of basketball players. Both groups have the same average height of 190 centimeters. However, in Group A, every player is exactly 190 centimeters tall. In Group B, some are 170 centimeters and others are 210 centimeters. The mean, or average, doesn't tell the whole story. We need a way to quantify how stretched or squeezed our data is. This is where measures of dispersion come in. Let's start with the basics, the deviation. To understand how spread out data is, we first look at the distance of each individual point from the mean. If we have a data point x and a mean mu, the deviation is simply x minus mu. But there's a problem. If we sum all these deviations, the positive and negative values cancel each other out, resulting in 0. This provides no information about the spread. To solve the cancellation problem, we square each deviation. This makes every value positive. Variance, denoted by the Greek letter sigma squared, is the average of these squared deviations. Mathematically, it is the sum of x minus mu squared divided by the number of observations n. By squaring the numbers, we also give more weight to outliers, effectively penalizing values that are far from the center. However, variance has a major practical drawback: the units. If our original data was in meters, the variance is in meters squared. If we are talking about dollars, variance is dollars squared. This makes it very difficult to visualize or explain in the context of the original data. It is a mathematical powerhouse, but a conceptual nightmare for simple communication. This is where the standard deviation steps in. By taking the square root of the variance, we bring the measure back to the original units of our data. Standard deviation, or sigma, tells us on average how far each point lies from the mean in a way that is easy to understand. It is the most popular measure of risk and variability in science and finance. In a normal distribution, also known as the bell curve, the standard deviation is incredibly powerful. The empirical rule, or the 68-95-99.7 rule, tells us that 68% of data falls within one standard deviation of the mean, 95% within 2, and 99.7% within 3. This allows statisticians to predict the probability of future events with remarkable precision. You might notice that sometimes we divide by n and sometimes by n-1. This is the difference between a population and a sample. When we only have a small subset of a larger group, we use n-1, known as Bessel's correction. This adjustment compensates for the fact that a sample usually underestimates the true variability of the whole population. In summary, variance is the squared average of distances, useful for mathematical modeling and penalizing outliers. Standard deviation is the square root of that variance, bringing us back to reality with the original units. Together, they provide the full picture of data volatility. Thank you for watching this masterclass on statistical dispersion. References: 1. J. L. DeVore, Probability and Statistics for Engineering and the Sciences. 2. Moore and McCabe, Introduction to the Practice of Statistics. 3. John E. Friend, Mathematical Statistics.